Hi, everyone. So I'm going to be talking to you about some work we've been doing in the Williams Group, looking at structure-activity relationships in series of catalysts for various different sustainable polymerizations. Really, the overarching motivation of this work is to develop more sustainable methods of making materials, and in particular polymers, because our current method of polymer production is largely unsustainable, using these high embedded emission petrochemically derived raw materials as monomers, and producing a polymer that's chemically inert and therefore difficult to recycle. So ideally, we'd move away from this kind of linear type materials production process to a more circular one, where the monomers are bio or waste derived, and the resulting polymer is functionalized so as to facilitate low energy chemical and mechanical recycling. So in this talk, I'm really going to be focusing on this forward direction in the circular materials process, how we can substitute for petrochemically derived monomers with bio or waste derived monomers like carbon dioxide. So one of the methods we look at to do this is via the ring opening copolymerisation of epoxides and CO2 as a method of generating aliphatic polycarbonates. And this reaction is gaining significant interest because it allows for high CO2 incorporation into the polymer, and also the polycarbonate product finds applications in the synthesis of polyurethanes and also in CO2 derived surfactants. I'll also be looking at the related ring opening copolymerisation of epoxides and anhydrides as a well-controlled route to polyesters, with applications in packaging and clothing, for example. But one of the most significant advantages of using processes like these to make polymers is the diversity of chemical structures and therefore polymer properties that are achievable through varying the substituent R using different commercially available epoxides and anhydrides. And the particular epoxides and anhydrides I'll be focusing on in this presentation are for the epoxides, cyclohexene oxide or CHO, and propene oxide or PO, and for the anhydride, phthalic anhydride or PA. And all three of these monomers are commonly used benchmark monomers in this field of polymerisation catalysis. Bio-based routes to all three are known and reported in the literature, and they're all three commercially available. But in order to achieve the fast, controlled, and selective synthesis of polymers using these monomers, a high-performance catalyst is essential. That's really the focus of this presentation. So in our group, we look at these well-defined homogeneous molecular catalysts that are heterodinuclear. So they contain binding sites for two metals that are different. And recently, we've been looking at this kind of match cyclic ligand, which contains a shift-based binding site for a transition metal like cobalt and a crown ether binding site for a group 1 metal. And this series of cobalt-3 group 1 metal catalysts was screened for various different epoxide CO2 copolymerizations, and it was found that the cobalt-potassium combination was the highest performing in each case. But at this point, we were really yet to understand the origins of its high performance, and in particular, whether there are any catalyst structural features that we could relate to high performance, so high activity or high selectivity polymer. And understanding these kinds of structure-activity relationships, as has been discussed in prior talks, is really important if we're going to further understand these catalyst systems and also rationally improve them in future. So the work I'm going to present to you today looks at this related series of cobalt-3 S-block metal heterodinuclear catalysts. So we're now not only looking at group 1 metals like sodium and potassium in the crown ether binding site, we're also looking at group 2 metals like calcium, strontium, and barium. And the idea is to systematically screen this series of catalysts for various different combinations of these monomers of interest in order to further understand these heterodinuclear systems and potentially draw out structure-activity relationship. But before I show you the results of the catalyst testing, I wanted to briefly outline how we measure our kinetic parameters and how we monitor these reactions. So we monitor the reactions using operando IR spectroscopy, which enables us to track absorbance as a function of time for various different carbonyl stretching frequencies. So in the case of this epoxide anhydride copolymerization, we can monitor the increase in polyester concentration by the increase in absorbance of the peak at 1730 wave numbers. We can also monitor the decrease in anhydride or monomer concentration by the decrease in absorbance of the peak at 1780 wave numbers. We're then able to calibrate these absorbance versus time measurements to conversion or concentration versus time data by integration of an NMR spectrum of an aliquot taken at the end of the reaction. And that enables us to construct these sorts of concentration time plots. So in this case, the reaction is zero order with respect to PA or anhydride concentration, which means this plot of PA concentration versus time is linear. And then our measure of activity, our observed rate coefficient, or KOBS, comes from the modulus of this gradient. The procedure for CO2 is very similar, so we can monitor the increase in polycarbonate concentration by the increase in absorbance of the peak at 1750 wave numbers. We then calibrate these absorbance time data to concentration time data, and in this case, we're looking at the concentration of the epoxide. So the reaction is first order with respect to the epoxide, CHO, which means the semi-logarithmic plot versus time is linear, and then our observed rate coefficient comes from the modulus of the gradient. So these are the results of the catalyst screening for the copolymerization of CHO and PA. And the first thing to note is that all 5 catalysts are successful at making a polyester with narrow dispersity. So that's indicative of well-controlled polymerization catalysis in each case. However, we can see that there are significant differences in catalytic activity across the series, as quantified by the turnover frequency and the K-obs. And most notably, the cobalt-3 group 1 metal catalyst significantly outperformed the cobalt-3 group 2 metal catalyst. And of the group 1 metal catalyst, the sodium and potassium, the cobalt-potassium combination is the most effective. So in order to further understand or rationalize these results, we plotted these activity values versus the S-block metal Lewis acidity, as quantified by the pKa of the corresponding S-block metal aqua complex. So those x-axis values are taken from the literature. And what we see is this exponential increase in catalytic activity with decreasing S-block metal Lewis acidity or increasing pKa. And we can rationalize this correlation with respect to the proposed catalytic mechanism, which is supported by experimental and computational investigations on related systems. And what we can see, this involves the rate determining step where the epoxide is activated by cobalt, which is then ring opened by this S-block metal bound carboxylate nucleophile that forms an alkoxide intermediate, which can undergo rapid insertion of the anhydride to reform the carboxylate, which then shuttles back on to the second S-block metal. So we can rationalize the trend by considering the rate determining step, and in particular, this key rate determining intermediate, which is this metal carboxylate species, by the fact that the least Lewis acidic S-block metals, so sodium and potassium, most effectively labelize this metal carboxylate bond, which activates it towards ring opening of the epoxide, that then decreases your transition state barrier and increases catalytic activity with decreasing S-block metal Lewis acidity. Also from these results, we can gain some insight into the distinct roles of the metals in the polymerization mechanism by the fact that the least Lewis acidic S-block metals, so sodium and potassium, are most effective. It implies that the S-block metal does indeed bind the carboxylate nucleophile rather than the epoxide electrophile, because if the S-block metal was to bind the electrophile, we'd probably expect the most Lewis acidic S-block metals to perform the best. So the same series of catalysts were also tested for the copolymerization of CHO and CO2 at 20 bar CO2 pressure and 50 degrees. And again, all 5 catalysts were successful in making a polycarbonate with narrow dispersity. But again, we see significant differences in catalytic activity across the series, with the cobalt-potassium combination being the highest performing. So if, as before, we plot these activity values versus the S-block metal Lewis acidity, we see a similar type exponential correlation. And similar to before, we can rationalize this exponential correlation with respect to the proposed catalytic mechanism, which now the rate determining step involves ring opening of a cobalt-bound epoxide via a metal carbonate nucleophile that produces this alkoxide intermediate, which can undergo rapid and reversible CO2 insertion to reform the carbonate. So if we can consider our rate determining step and our key rate determining intermediate, which is this carbonate species, the least Lewis acidic S-block metals, sodium and potassium, are most effective because they most effectively labelize that metal carbonate bond, activating it towards ring opening of the epoxide, which increases your catalytic activity. We also tentatively propose that the non-linear nature of the trend arises due to the fact that the carbonate nucleophile can bind to the S-block metal via multiple coordination modes. So it can bind via a monodentate or a bidentate coordination mode, and potentially that gives rise to a reinforcing effect with changing S-block metal Lewis acidity and could give rise to non-linearity in the correlation. I should mention this is not the first time that we've seen these kinds of exponential activity-acidity correlations. We've also seen it for the same series of catalysts when tested for a different epoxide, so propene oxide instead of cyclohexene oxide, in the case of the copolymerization of PO and CO2, And in the case for PO and PA, we also see exponential increases in catalytic activity with decreasing S-block metal Lewis acidity. We're also interested in investigating the effect of operating conditions on the activity-acidity correlation, and in particular, the effect of decreasing the CO2 pressure from 20 bar to 1 bar CO2, as 1 bar CO2 is a more energy efficient and industrially applicable pressure to work with. So the same series of catalysts were tested for the copolymerisation of CHO and CO2 at 1 bar CO2 pressure, and again, significant differences in catalytic activity were observed across the series, with the cobalt-potassium combination being the highest performing. So if, as before, we plot these values versus the S-block metal Lewis acidity, we see that the correlation is more linear in nature. So just as a side-by-side comparison, for the same series of catalysts for the same reaction, the copolymerisation of CHO and CO2, at 20 bar CO2 pressure, the activity-acidity correlation is nonlinear or exponential, but at 1 bar CO2 pressure, the correlation is linear. But this is not the first time that we've seen linear activity-acidity correlations. We've also seen it for the same series of catalysts for the ring opening polymerization of lactide. And here we tentatively rationalize the linear correlation with respect to the proposed catalytic mechanism and the key rate determining intermediate, which involves ring opening of a cobalt-bound lactide by this S-block metal alkoxide nucleophile. And we hypothesize that the linear activity-acidity correlation relates to the alkoxide nature of the key rate determining intermediate. But just to kind of reiterate that, in the cases where we have a carbonate or carboxylate key rate determining intermediate, we propose that links to nonlinear activity-acidity correlations. But in the case of the ring opening polymerization of lactide, the key rate determining intermediate is an alkoxide, where the nucleophile could only bind to the S-block metal in a monodentate coordination mode. Potentially that gives rise to a more stepwise increase in catalytic activity with decreasing S-block metal Lewis acidity, and therefore the correlation is linear. So perhaps we can use this idea to rationalize why we see a linear activity-acidity correlation for the copolymerization of CHO and CO2 at reduced CO2 pressure. So of course there is an alkoxide in this catalytic cycle, but the kinetics plots do not suggest that there is a formal change in rate determining step from epoxide ring opening to CO2 insertion at lower CO2 pressure. But it's still possible that this intermediate becomes increasingly important in governing the relative rates across the series, because you bias your CO2 insertion equilibrium towards the alkoxide at lower CO2 pressure. So tentatively, we propose that you can gain some insight into the relative balance of the key intermediates in the catalytic cycle from performing this structure activity investigation at different carbon dioxide pressures, where at 20 bar CO2 pressure, our key rate determining intermediate is this carbonate species, gives rise to a nonlinear trend, whereas at reduced CO2 pressure, our alkoxide becomes more important, and we see that by the fact that the activity-acidity correlation is now linear. But this hypothesis is quite early stage at the moment and requires further substantiation, and that's the topic of ongoing work in our group at the moment. So to conclude, I presented a series of structure activity correlations as applied to this series of heterodinuclear cobalt-3 S-block metal catalysts for various different copolymerization reactions. I've also tried to draw out how we can use these structure activity relationships to gain insight into the high performance of the cobalt-potassium combination and the distinct roles of the metals in the polymerization mechanism, and also potentially the balance of the key intermediates in the catalytic cycle and how those might change with reaction conditions. But there's a lot of work still to do on this area, so we'd like to further prove the generality of these correlations for different catalysts and different polymerization reactions. And in particular, we're looking for a new x-axis, so like a new measure of S-block metal Lewis acidity, or an additional catalyst structural parameter that we can correlate to catalytic activity that crucially is measured within our specific complex rather than a pKa value taken from the literature. And that's also the topic of ongoing work in the group at the moment. So with that, I'd like to thank my supervisor, Charlotte, for her help and support and for making this work possible. I'd like to thank Fran, who did a lot of the early work and first uncovered these correlations. I'd like to thank my whole group for their help and support. I've put a QR code to the full published work that I've presented to you today in case anyone would like a further read. And I'd like to thank you all for your attention.
Thank you, Fred. Questions? Lily?
Thank you. Very nice talk. As you mentioned at the end of your talk, the Lewis activity might not be the only parameter that varies in your compound. And one thing I was wondering about specifically was ring size effects.
Yeah.
You're offering the S block metals the same 18 crown 6 motif, and they all have different radii and different fits to that motif. So
Yeah.
is that a fair comparison, or is it maybe just a reflection of how well they fit into that ring?
Yeah, that's a really good question. So we have tried to plot binding constants of the S block metal in a 18 crown 6 model versus catalytic activity, and they don't correlate. We haven't measured the binding in our specific catalyst system. However, we have looked at changing the crown ether size, for example, making it smaller for like a 15 crown 5 unit that you think sodium would be better suited for, but it doesn't improve the catalytic activity versus this 18 crown 6.
For
So,
the same metal? Sodium.
Yeah. The sodium in 18 crown 6 versus sodium in 15 crown 5 does not improve. It actually worsens catalytic activity and makes the complex very hard to make. So it's slightly, we had this exact same thought, and it's a really interesting point, but we think perhaps binding affinity is not the key parameter. That
The geometry of it.
Yeah, it could also be due to elevation above the plane. So we've tried putting bigger metals in, like rubidium and cesium, which have higher pKa values. So you'd think they would improve the catalytic activity, but they're much worse. And we hypothesize that's because it binds very out of the plane of the crown, dimerizes in the crystal structure. So yeah.
Interesting. Thank you.
In which case, I think we will finish today by thanking all of the speakers. Excellent series of lectures. Thank you.